Hello my dear friends, welcome back to my YouTube channel. In this class I am going to start a new chapter, that is chapter on entropy, which is an all important topic both for GATE and university exam point of view. Questions are often asked from this chapter, and it is also a relatively top subject, but once you grab those concepts related to entropy, it will be very easy for you to solve the problems or answer the conceptual questions that are often asked in the examinations. So before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. You see, second law of thermodynamics often lead to expressions which involve some inequalities. Second law may we find some inequalities. For example, we say that the efficiency of a reversible heat engine is higher than that of an irreversible heat engine between two given temperature limits. We know that if suppose the high temperature is TH and lower temperature is TL, and two engines are operating between these two temperature limits, one is reversible and other one is irreversible, obviously the efficiency of reversible engine will be higher than that of the irreversible engine. That's what the Carnot theorem states. So this is an inequality. This is an inequality. The efficiency of one heat engine is less than, or efficiency of one heat engine is greater than the other. So that this is really an inequality. Another example of inequality of second law is the COP of reversible refrigerator or heat pump is higher than that of irreversible refrigerator or heat pump between two given temperature limits. This is also an inequality. COP of reversible refrigerator is higher than that of irreversible refrigerator between two given temperature limits. Another inequality which is also very important, having larger consequences in thermodynamics, is the Clausius inequality. And this Clausius inequality was stated in 1865 by German physicist R.J.E. Clausius, and who is also one of the founders of thermodynamics. You know, this Clausius, R.J.E. Clausius, was also one of the founders of thermodynamics. And what is this inequality? This inequality is nothing but the cyclic integral of del Q by T is less than or equal to 0. The cyclic integral of del Q by T is less than or equal to 0. You know, what is this del Q? Del Q represents the differential amount of heat transfer. Always you see, if you integrate this term over a cycle, this will yield this following result. And one of the important thing is that this Clausius inequality is valid. This Clausius inequality is valid only for cycles. Only for cycles. That is both reversible as well as and irreversible. Both for reversible cycles and for irreversible cycles, this Clausius inequality is valid, and it is not valid for any kind of process. And the questions are also asked for what this Clausius inequality is valid. In fact, the answer should be it is valid for both reversible as well as irreversible cycles, and it is not valid for any process. And you see why this cyclic integral is carried out and what does this represent. Always heat transfer to or from a system can be considered to consist of differential amount of heat transfer. So if you add all those differential amount of heat transfers, you will find the total heat transfer. And if you add all those del Q, and T represents the boundary temperature at which the heat transfer takes place. Heat transfer takes place means there must be temperature difference, but T represents the temperature at the boundary where the heat transfer takes place. And if you add all these terms, differential dQ by T or del Q by T, then the same result will be obtained as you find through integration. Integration means summation of all those differential amount of heat transfer divided by the temperature of the boundary. So this Clausius inequality can be proved in two different ways, and the first one is like this. You see, this is a reversible cyclic device which extracts del QR amount of heat, from a thermal energy reservoir which is at a higher temperature TR. And this cyclic device, reversible cyclic device, this by extracting this heat, it produces del W reversible in a infinitesimal amount of time dt. These things happens. That's why these del terms are coming into picture. Otherwise QR and WR kind of things would have come, but since we are considering the process during an infinitesimal time period, suppose dt, small time period dt, then that's why we are taking del QR and del W reversible, etc. terms. So, and del Q is the heat that is transferred to a system, and T is the temperature of the boundary while this heat transfer takes place. And this T is not constant, but this TR is constant. We know whatever amount of heat you may extract from a reservoir, its temperature doesn't change, but this T is variable. But during that process, during that small time period dt, this temperature remains constant. But one of the important thing is we have to remember that this T is a variable, but for small time period dt, this T can be assumed to be constant. And by supplying this del Q amount of heat, which is rejected by this, whenever a heat engine produces work, it rejects some amount of heat. Otherwise, the Kelvin Planck statement will be violated. So a heat engine has to exchange heat with two reservoirs. Then only it can produce work. So you see, del Q is the amount of heat that is supplied to the system, and with this heat, this system produces. Whenever an energy is supplied to a system, it is converted to another form, and so this system produces some amount of work, that is del W system. This is del W reversible heat engine, and this is del W system. And you see, we will consider this dashed line to be the boundary of a combined system, and we can consider this reversible heat engine and this system to consist a combined system. This is your combined system. So you see, since this is in fact you see, by applying the first law or applying the energy balance to combined system, you see, this is the energy supplied. E in, this is the principle of energy balance. E in minus E out is equal to delta E. Whenever we are supplying E in amount of energy to a system and we are extracting E out of the system, the net energy will be accumulated and it will be stored in the system, and that will be delta E. So E in this case, E in is del Q. If you consider this combined system, you see, if you consider this combined system and do the energy analysis, E in is del QR. If you consider the combined system and conduct the energy analysis, del QR is the energy supplied minus E out is, what is the energy going out of the system? What are the terms in which arrow sign is away from the system? This is del W reversible plus del W system. I can take, this is del W of combined system is del W reversible plus del W system. And in E out, I can write del WC. Work done by the combined system. Combined system means reversible cyclic device and system, both are taken together. And you see, we are doing energy analysis for the combined system, not for this individual system. This is for combined system, we are doing energy analysis. Del QR is the energy supplied to this combined system. This is the boundary of the combined system. And work done by this combined system is del W reversible plus del W system, or I can take del WC for that. So change in energy, I can take DEC. Change in energy of the combined system, DEC. Since these are path function terms, so delta is taken for them, and since it is an exact differential, D term can be taken. DEC, change in energy of the combined system, DEC. And this is suppose equation 1. And for this is a reversible heat engine. This is a reversible heat engine, and this del QR is the heat supplied to this engine, and del Q is the heat rejected by this reversible heat engine. So according to the thermodynamic temperature scale, del QR divided by TR equal to del Q divided by T, because QH by TH is equal to QL by TL. And the sign of del QR is considered with respect to this reversible heat engine, and the sign of del Q is considered with respect to this system. Whenever del Q is added to the system, it is taken to be positive, and when del Q is removed from the system, it has to be taken negative. And when del QR is supplied to this reversible heat engine, it is positive, and that is the convention. So this is suppose this is equation 2. This is equation 2. And by eliminating del QR from equation 1 and 2, you see, from equation 2, del QR will be del Q multiplied by TR divided by T from equation 2. And substituting this value of del QR in this equation 1, we get, substituting the value of del QR in equation 1, we get del Q TR divided by T minus del WC equal to DEC. So from this, I can take del WC is equal to del Q TR divided by T minus DEC. So this is the equation. By eliminating by substituting the value of del QR from equation 2 and putting in equation 1, we get this equation. Suppose equation 3. Supposing that this system completes a cyclic process, completes a cycle, and this is since when it completes a process during dt time, it is completing already a cycle. So whenever it completes a cycle, it will complete an integral number of cycles. It will complete an integral number of cycles. When this system completes a cycle, it will complete a integral number of cycles. So by integrating this over cycle, for a cycle change in property, any if you take the cyclic integral of any property, it will be 0, and energy is a property of system. So if you integrate this over cycle, you will find WC is equal to cyclic integral of del Q TR by T, and this term will be 0. Now cyclic integral of any property, suppose dV, cyclic integral of dP, all this property, cyclic integral of any thermodynamic property is 0. So whenever we are integrating both sides, cyclic integral of del WC becomes WC. This is the work over the cycle of the combined system. WC is the total work done by the cycle of the combined system. Whenever the combined system completes a cycle, this is the work done. So WC is this much, del Q TR divided by T, and this is 0 because cyclic integral of any energy is a property of system. So since TR is always constant, this can be taken to be outside, any constant can be taken outside of the integration side. So TR del Q by T. You see, WC represents the net work for the combined cycle. Net work for the combined cycle. So this is the final equation. WC is equal to TR del Q by T. Suppose this is equation 4. Equation 4. WC is equal to TR del Q, cyclic integral of del Q by T. You see, WC here cannot be positive. WC here cannot be positive because it cannot produce any work. WC means work done by the combined system during a cycle. You see, this is the combined system. This is exchanging heat only with one reservoir, that is at a temperature TR. So if it produces certain amount of work, net work output, it will violate Kelvin-Planck statement of second law of thermodynamics, because Kelvin-Planck statement of second law states that for a heat engine to produce net work output, it has to exchange heat with two thermal energy reservoirs. In this case, this combined system exchanges heat with only one reservoir, that is at a temperature TR. Not any other reservoir is there, because this is the combined system and this is extracting heat only del QR from one thermal energy reservoir. So where is the another reservoir to which it is extracting heat? It is rejecting heat. There is no other reservoir. So it violates Kelvin-Planck statement of second law of thermodynamics. So WC can't be positive. No positive work cannot be produced. WC can't be positive. You see, this is the equation we derived. WC is TR del cyclic integral of del Q by T, and this cannot be positive, because if WC will be positive, Kelvin-Planck statement of second law will be violated, because if WC is positive means del W reversible plus del W system will be positive. That means a cycle, this system completes a cycle and produces some net work output, but exchanges heat with only one reservoir, that is at TR, which is violative of Kelvin-Planck statement of second law of thermodynamics. So WC cannot be positive, can't be positive. That means no net work can be produced here, because that will violate Kelvin-Planck statement of. So WC can't be positive. But from equation 4, we have already derived that WC is nothing but TR multiplied by cyclic integral of del Q by T. But TR is always positive. Temperature is always positive. So if WC can't be positive and TR is already positive, so del Q by T cannot also be positive, because del Q by T, cyclic integral of del Q by T cannot be positive, because ये अगर पॉजिटिव होगा और ये पॉजिटिव है, तो पॉजिटिव मल्टीप्लाइड बाय पॉजिटिव will produce a positive value. But this can't be positive means, and this is positive, this is definitely positive TR. So del Q, cyclic integral of del Q by T cannot be positive. Hence, cyclic integral of del Q by T can't be positive. Can't be positive. That means cyclic integral of del q by t cannot be positive, means it is less than or equal to 0. It is less than or equal to 0. And it is valid both for, this inequality is valid for both for reversible and irreversible cycles. Since it cannot be positive, means it has to be either negative or 0. That means less than or equal to 0. Suppose this system, whenever this system completes a cycle, supposing that there is no irreversibility within system, no dissipative effects or friction effects within this system during that cyclic process. This is already we have assumed to be a reversible heat engine. Suppose here also there is no element of irreversibility, and in this system also there is, suppose, no irreversibility is there. That means this will be a case of internal reversible cycle. Internal reversible cycle. So what will happen? Internal irreversible cycle. Internal reversible cycle. Internal reversible cycle. So you see, if we'll take the case of internal reversible cycle, for normal cycle WC cannot be positive because it will violate, suppose internal reversible cycle means, why internal reversible? Because we suppose there is no element of irreversibility in this case system also. Already we have assumed this to be a reversible cycle. So our combined, if there is no element of irreversibility in this system, this complete combined system will undergo a reversible cycle. So that means if WC cannot be positive, and in case of a reverse cycle what happens, or if the work done in original cycle is positive, then the reversed cycle, in case of reversed cycle, the magnitude will remain same but the sign will be different. So if WC amount of work is produced by a normal cycle, then same WC amount of work will be consumed by the reversible cycle. So if this is positive, then the work interaction for the reverse cycle will be same magnitude but opposite sign, that will be minus WC. So for reversible, so you see WC for normal cycle, since we have discussed that WC for these normal cycles cannot be positive because this will violate this combined cycle में जो WC होगा वो पॉजिटिव हो नहीं सकता क्योंकि दिस वायलेट्स केल्विन प्लैंक स्टेटमेंट. नो नेटवर्क आउटपुट कैन बी प्रोड्यूस्ड बाय दिस साइकिल. एंड इफ इट इज ए internally reversible cycle means we can reverse the cycle, but in case of irreversible cycle we can't reverse the cycle, but in case of reversible cycle we can reverse the cycle. So if in case of a normal cycle WC cannot be positive, so WC for internally reversed cycle cannot be negative, because in case of reverse cycle only magnitude remains same but only sign changes, positive negative हो जाता है. So since in normal cycle it can be positive, in case of reversed cycle it cannot be negative. So what value it will assume? It will assume only the value is 0. So WC internally reversible cycle is equal to 0 only. It can assume only 0 value. So from the equation what we have already derived is, so if WC is 0, since TR cannot be 0, TR is always positive value. TR is the thermal energy temperature of higher thermal energy reservoir. So del Q by T, WC is equal to TR multiplied by cyclic integral of del Q by T. That means this is 0, implies cyclic integral of del Q by T is equal to 0, and this is valid only for reversible cycle. So from this inequality, del Q by T is less than or equal to 0. This del Q by T equality is for reversible cycles, and this inequality less than. That means del Q by T is equal to 0 for reversible cycle. Reversible cycle. And del Q by T less than 0, this is valid for irreversible cycle. That means in case of irreversible cycle, we can't reverse it. So only in case of irreversible cycle, work done cannot assume any positive value. So that's why del Q by T cannot also assume any positive value. So that's why del Q by T will be either less than or equal to 0. So for irreversibles, equal to 0 will be valid only for reversible cycle. That we proved here. If in case of a normal cycle, it can be positive. For a reverse cycle, it can be negative. So that's why what value it can assume is only the 0 value. So if it is 0 means del cyclic integral of del Q by T is also 0. So this can also be proved alternatively, that is like this. You see, another way to prove this cyclic integral of del Q by T is less than equal to 0 is, suppose there are two thermal energy reservoirs, TH and TL. Here suppose one reversible heat engine is operating and another irreversible heat engine is this is reversible heat engine and this is irreversible heat engine. Both are extracting suppose same amount of heat QH. This is also extracting QH, and both, this is irreversible heat engine and this is reversible heat engine. So this is suppose QL for reversible and this is QL for irreversible heat engine. Suppose same amount of heat is supplied to these two heat engines, and this produces W reversible and this is W irreversible. You know, according to Carnot theorem, the efficiency of reversible heat engine is greater than irreversible heat engine, efficiency of irreversible heat engine, whenever those two heat engines operate between same two temperature limits. So this is Carnot theorem. Efficiency of reversible heat engine is greater than efficiency of irreversible heat engine. You know, efficiency is nothing but work output divided by heat supply. So WR divided by QH is greater than WI और irreversible divided by QH, क्योंकि heat supplied दोनों cases में same है QH. So from this what we find is WR is greater than WI or irreversible. This is irreversible. You know, according to energy balance principle, WR is QH minus QL. Total energy that is supplied to the system during the cyclic process is QH, and these two energy go out of the system during the cycle. So QH is equal to W plus QL. That means W is equal to QH minus QL. So WR, in place of WR, I can write QH minus QLR greater than QH minus QLI. Irreversible. That means QLI is greater than QLR. That means heat loss or heat rejected in case of irreversible heat engine will be higher than the heat rejected to low temperature reservoir. ये जो heat ये waste हो रहा है, and wastage of heat is higher in case of irreversible heat engine if you compare that with the reversible heat engine. क्योंकि QL ज़्यादा हो रहा है तो वर्क आउटपुट लेस आ रहा है irreversible engine में, क्योंकि एफिशिएंसी तो लेस है, एफिशिएंसी लेस है मतलब वर्क आउटपुट लेस आ रहा है, इसीलिए एफिशिएंसी लेस आ रहा है. So QL irreversible is greater than QL reversible. If you calculate cyclic integral of del Q by T for reversible cycle, it is nothing but QH by TH. ये समेसन हम कैलकुलेट कर रहे हैं, डेल क्यू बाई टी का समेसन. साइक्लिक इंटीग्रल ऑफ डेल क्यू बाई टी फॉर रिवर्सिबल साइकिल मीन्स वी विल ऐड दिस टू टर्म्स, क्यू एच बाई टी एच एंड क्यू एल बाई टी एल. Magnitude wise QH by TH for any reversible cycle, you know QH by TH is equal to QL by TL magnitude wise, but साइन दोनों का डिफरेंट आएगा. अगर 10 किलो जूल हीट ये सिस्टम को साइकिल के अंदर आ रहा है तो 10 किलो जूल डिवाइडेड, ऑब्वियसली नॉट QH इज नॉट इक्वल टू QL, ओनली QH डिवाइडेड बाई TH is equal to QL by TL magnitude wise. But if you take the sign into consideration, QH by TH, whatever, suppose this is plus X, and then this QL by TL will come out minus X, because magnitude wise दोनों same है, QH by TH is equal to QL by TL. But if this is plus, because this heat is added to the cycle, this heat is added to the cycle, and this heat is rejected from the cycle, so this will come out negative. So if you add those two values, this will yield 0, because suppose this is 10 kilojoule per Kelvin, this is also 10 kilojoule per Kelvin, but this while taking the sign into consideration, this will be minus 10, this will be plus 10, and if you add those two values, this will come out to be 0. So cyclic integral of del Q by T for a reversible cycle is equal to 0. So for an irreversible cycle, you see, for an irreversible cycle, cyclic integral of del Q by T for an irreversible cycle is QH by TH minus QLI divided by TL. You know, this QH by TH is same as, this QH by TH is same as QLR by TL, because QLR stands for heat rejected to the low temperature reservoir in case of reversible heat engine. So QH by TH, in place of QH by TH, I can write QLR divided by TL minus Q, minus sign क्यों हम लिख रहे हैं? Because in the, when heat is rejected from the cycle, we have to take it as negative. Sign, we have to take the sign positive when it is applied to the cycle, to the heat engine, and when it is rejected, this term has to be taken, the sign has to be taken as negative. So QLI divided by TL, this is equal to QLR minus QLI divided by TL. Since we have already discussed that QLI will be always greater than QLR. QLI is always greater than QLR. So this is a smaller value and this is a larger value. So smaller value minus larger value obviously will yield a negative value. So this will come out numerator. In numerator you will find a negative value, because QLI, heat lost in case of irreversible engine, is always higher than, heat lost means heat rejected to the low temperature reservoir, is always higher in case of irreversible heat engine, and the corresponding value will be less in case of reversible heat engine. So that's why when you subtract a large value from a small value, you will find a negative answer. So in numerator you will find a negative term, and TL cannot be negative, so negative divided by positive is negative, so this is 0. So what we found is cyclic integral of del Q by T for irreversible heat engine is less than 0, and cyclic integral of del Q by T, cyclic integral of del Q by T, in fact this is negative because magnitude wise दोनों same है, लेकिन if you take, this is put minus sign before this, QH by TH minus QL by TL, this will be 0, because QH by TH is equal to QLR by TL, sorry. So that means cyclic integral of del q by t for reversible heat engine is 0 and cyclic integral of del q by t for irreversible heat engine is less than 0. So the complete inequality is cyclic integral of del q by t is less than or equal to 0, and this is valid only for cycles, not for any kind of process, and this is valid for both reversible as well as irreversible cycle.